In this lesson, we will discuss linear regression as a modeling process. We will use this topic as motivation for neural networks. Regression is a fancy name for a modeling process. In particular, with linear regression, we will create a model that helps us to predict a quantitative or numeric output variable from one or more input variables. These input variables can be quantitative or categorical, though we will need to distinguish categorical variables when we use Python to conduct linear regression. In general, when conducting linear regression analyses, the software is using calculus behind the scenes to optimize values for the slopes and intercepts of the line by minimizing a value called the sum of squared error, or the mean squared error. The error term is the difference between predictions from our model and the actual values observed in the data. We find these error values, square them, and sum them together to get the sum of squared error. Taking partial derivatives with respect to all slopes and intercepts in the problem and solving the simultaneous set of equations give us a set of values that optimize or minimize the error in our process. In statistics, this process is often referred to as finding the ordinary least squares line, or OLS. Let's take a look at a motivating example for using linear regression. Suppose that we want to predict a person's ideal mate height given their own height. In this case, the ideal mate height would be our response or outcome variable. In regression, we usually only have one outcome variable in a problem, and for linear regression, this variable should be quantitative. The person's own height value is what we will call the predictor or input variable. In our current example, we only have one input variable, but we will change the problem in just a bit to include a second predictor variable. So our goal is to create a model that provides us with a predicted ideal mate height. This will be equal to some y-intercept, which we're denoting here as b, plus the person's height times the slope value, which we're denoting here as w1. You should note that this equation will not be perfect at predicting every person's ideal mate height, and we could model the actual ideal mate height as the predicted value plus or minus some error term. This is the same error term discussed on the previous slide that we wish to minimize. Now that we understand the problem, we can start working with Python in Google Colab to find a model for our problem. To begin, we first must load the file into Colab and change it to a bytes.io type. From there, we can utilize the read_CSV function from the pandas package to read in the data. If you're working on your personal machine instead of Google Colab, you do not need to conduct the first two steps provided here. However, you will need to provide the appropriate file path on your computer with the read_CSV function instead of the bytes.io object that I've input here. Utilizing the head function in Python, we can see the structure of our data. For each individual in the data set, we know their sex, height, and ideal mate height. It might be helpful to graph the data to get a better idea of the relationship that exists between height and ideal mate height. In the graph on the screen, the person's height is on the x-axis and the ideal mate height is on the y-axis. We will generally use this convention when creating models. That is, the value that we wish to predict will be on the y-axis, and one or more of the variables that we're trying to use as predictors will be on the x-axis. Note that to create this graph, I first needed to import the matplotlib pyplot application. While it wasn't necessary, I extracted the height and mate height variables from my data frame to make for easier plotting. Finally, I used the plot function from matplotlib to create the scatter plot of the data. In looking at the output, it would appear that there's a negative trend between height and mate height. That is, as height goes up, ideal mate height goes down. Now we can conduct our linear regression analysis. We will need to import the stats model package, specifically the OLS function, to conduct our ordinary least squares regression analysis. As we will do many times this semester, we need to build the model that we would like Python to use to estimate parameter values. To do this for the regression analysis, we will call the OLS function. Within this function, we need to specify the form of the model that we would like to create. In particular, the syntax for this requires that the output variable, Mheight, is listed first, and the predictor variables are listed after the tilde. We also provide the data frame from where we will be grabbing the data. After telling Python the structure of the model, we need to fit the model. Finally, we print the summary of the model to the screen. There's a lot of information provided in the output, but for our purposes, we just need the information that corresponds to the coefficients for the intercept and height variable. These will tell us the values of b and w1 from the formula we provided earlier. We will be able to extract these values directly, so we should note the order that they're provided in the summary. The rest of the information here has its purposes in statistics, but we will not be using that information here. Going back to the scatter plot of the data that was created earlier, we can add the least squares regression line. To do this, we first recreate the scatter plot and then add a line to the graph using the plot function. The inputs to this function are the values on the x-axis that we wish to use, or in our case, the values of height. It also takes in the value of y that corresponds to those heights. Note that the params array contains the values of the y-intercept and the slope that we found in the previous screen, in that order. We can extract the values from the params array and use them to calculate the values on the least squares line for each of the heights. We can then confirm that there's a negative trend to the data. As the heights go up, the ideal mate height goes down. Now, thinking about the context of the data, that interpretation may not make the most sense to us. Do we really believe that someone that is very tall will want a very short mate? Something doesn't seem right about our model. There may be some missing information. Let's try modifying our model to include the sex of the original survey participant. Note that the variable sex was a categorical variable that had values of m and f for male and female. If we want to include this in our linear regression model in Python, we need to indicate that the variable is categorical. We do that with a capital C function around the sex variable. Also note that since we are adding another predictor variable to the model, it gets added on the right side of the formula that was provided earlier. Otherwise, our ordinary least squares function is unchanged. We again fit the model and print the summary to get the information provided on the screen. We should note now that there are three variables in our output. These include the intercept, the categorical variable for sex, and height. Even though we had input our variables in a different order, the predictor variables are listed in alphabetical order. Make sure to check the order of your variables if you plan on using the params array for predictions. Another thing to note is that the variable sex also included some extra notation. In particular, it's been amended as bracket t.m, close bracket. This tells us that the coefficient that's being provided should only be used in our equation if the individual that we're predicting for is male. Now we can recreate our scatter plot of the data, but we will now need to include color in our graphic to indicate whether the participant was male or female. This involves first making a dictionary that maps the different categories of sex to the different colors, and then telling the scatter function to apply that mapping when assigning color within the graph. Additionally, two lines have been added to this graph. For the males, note that the params1 value was added to the formula for prediction, resulting in a different line for the males and females within the graphic. Now we can see that there's a positive relationship between height and mate height. As a person's height goes up, their ideal mate height also goes up. Shorter people prefer shorter mates, and taller people prefer taller mates. The difference that we see now, though, is that in general, males prefer mates that are shorter than them, and females prefer mates that are taller than them. One of the pieces of summary information that can be extracted from each of the models that we have created here is called the mean squared error of the residuals, or just MSE. This is a value that is directly related to the error that we discussed earlier, when we're trying to minimize error between predicted and actual values. Within each of our models, the minimum value of the MSE was found with the data that was provided. However, we can see that the second model has a lower overall MSE because we were able to add another variable to our model that provided more information for predictions. In general, as we're creating neural networks this semester, our goal will be to reduce this overall error, and we can do that by adding more variables. One problem that we will run into, though, is that if you have thousands of variables that you're trying to consider as inputs to your model, then we'll have thousands of parameters that need to be estimated, and the calculus behind the scenes that was done here breaks. Instead, numeric methods called gradient descent will be used to work towards minimizing the error that is seen. We will talk more about this and methods used for gradient descent in a future video.